This is a quick review on chemical equilibrium. So here we have a reaction. So let's say this is at time A, and then after some time this happens. We have, let's call this one the reaction at time B, the reaction at time C, time D, time E, and also time F. So at time A, it's obvious that this reaction has not started yet because all of these are still the reactants. On this reaction, we'll be representing the reactants as blue and then the products as red. So here obviously we don't have any of the products, we only have the reactants. So on this case, let's make a reaction quotient. So here our quotient is based on the concentration. We'll base it on the concentration of the products over the reactants. So in this case, our concentration of the product, that's obviously 0. And then here we have, let's say 16, because here we have 16 particles of the reactants. So here the quotient is equal to, that's equal to 0. So on this case, this means that we don't have any of the products yet. So here the reaction quotient, or the QC, is equal to 0. Let's say after some time, at time B, we have this one. So let's make another reaction quotient. Again, this reaction quotient is based on the concentration of the products over the reactants. So here we have already two products, and then the rest are the reactants pa rin. So here, let's divide this one, 2 over 14. So 2 divided by 14, that's equal to 0.14. So here, the reaction quotient is 0.14. So here, when the QC is less than 1, it means that there are still more reactants on this case, because obviously pag less ang products, so mas less ang numerator compared sa denominator. So again, this numerator, that's the products, and then this one is the reactants. So pag less ang products, that means our QC is less than 1. Then pag mas dako ang products, then our QC will be equal to or greater than 1. Let's go to time C. So at time C, we have this one. So we have the reaction quotient here, that's 3. We have 3 products now, then the rest are the reactants pa rin. So here our QC, or the reaction quotient, that's equal to 3 divided by 13, that's equal to 0.23. So 0.23. So as you observe here, our value of QC increase as we increase our concentration of the products, right? So that's from 0.14 to 0.23. Now, at time D, so we have an increase of the products. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we have 10 products now. 10 products, then the rest are the reactants. We have 1, 2, 3, 4, 5, 6 reactants. So here the reaction quotient, that's equal to 10 divided by 6. Again, 10, that's the products, 6, that's the reactants. On this case, that's equal to 1.7. So 1.7 at time E. So after some time, we measure the concentration of the reactants and products. So here we have 1, 2, 3, 4, 5. That's actually 10. And then the rest is the reactants. So that's 10 over 6. So QC is still 1.7. This is 1.7. Then here at some time pa rin, we have this one. We have 10 products pa rin. Then we have 6 reactants. So here, the reaction quotient is equal to 1.7. Okay, so let's observe this reaction. At what time do you think the reaction reach equilibrium? Right, so it obviously reached on, so it started at time D because after some time, our concentration of the products and reactants remain constant after some time. So in this case, we say that the reaction has reached equilibrium at time D, and and on that case, the reaction quotient is equal to 1.7. So in this case, this 1.7 is constant throughout this one. So this is also the Kc, or the Keq, or this is the equilibrium constant on this case. Okay, so on this case, as you see here, there is still a reaction. So this reactants are still forming into products, and also this products are turning back into the reactant. So there are still chemical reactions happening here at time d. But why do you think the concentration of the products and reactants remain constant on this case? Okay, so that's because the rate of the forward reaction equals the rate of reverse reaction. So in this case again, the reactants are turning back into the products, and also the products are turning back into the reactants. So in this case, let's say in every second, 1 molar of the reactants are going or forming the products, and also at the same time, every second 1 molar of the products are turning into the reactant. So in this case, there is still a chemical reaction. So we still have the forward reaction, then we also have the reverse reaction on this case. But since the rate or the speed of forward reaction and then the reverse reaction are equal, there seems to be no change on the concentration of the reactants and products over time. So we also call this one as dynamic equilibrium. Dynamic equilibrium. So here it seems like there's no change on the concentration, but if you look closely on the individual particles in the reaction, there is still changes, so it's still dynamic. So our reactants are still changing to products, and the products are still changing into the reactants. So let's look at here. So let's say this reaction is at equilibrium. So we have, let's say, 6 molar of the reactants, then we have 4 molar of the products. And again, there's still a chemical reaction here. So there's still a reaction of the products, of the reactants forming the products, and then the products are still forming the reactants. So as you see here, there is a chemical reaction, but since here the rate of the forward reaction is equal to the rate of the reverse reaction, there seems to be no change on the concentration. So here we can still see here 6 molar of the reactants. Then here we still have 4 molars of the products, and as you see, this continues. So again, there is still a chemical reaction, but still, since there seems to be no change on the concentration. Here we have two reactions. Let's say these reactions are at equilibrium. So let's measure the KEQ on this case. So on the first reaction, we have 1, 2, 3, 4. Actually, we have 12. So we have 12 products over 4 reactants. So here the KEQ is equal to 3. On the other side, we have KEQ. So as you see here, there are more reactants compared to the products. So in this case, we only have 4 products, and the rest is the reactant. So that's 4 over 12. That's equal to 0.3. So now let's observe here. So as you observe here, when KEQ is greater than 1, it favors the forward reaction. So it means that there are more products compared to the reactants on this case. And then on this case, the KEQ is less than 1. So when the KEQ is less than 1, it means that the reaction favors the reverse reaction, because as you see here, there are more reactants compared to the products. And also it's very obvious, right? Because again, this numerator represents the product, and then this denominator represents the reactant. So obviously when there is less product, then this would be smaller, and so therefore the answer would be less than 1. And then if we go on this side, since there are more products here, then this number is bigger compared to the denominator. And so if there are more products, or if this is larger compared to the denominator, then KEQ is greater than 1. So again, our KEQ tells us the direction, uh, or whether our reaction favors the forward or the reverse reaction. So when I say it favors the forward reaction, it means there are more products compared to the reactants on that reaction. Then when I say it favors the reverse reaction, it means that there are more reactants compared to the products on that reaction.